this point, we've gone through all the data preparation things. We've got our composite fingerprints. We've looked at the composite fingerprints to see how well they can discriminate. And we've also kind of looked and seen what our likely sediment sources are. We're actually at the point now where we can start doing the mixing model part of things.
Yeah.
I won't go into exactly how these work, just because it's quite a complicated thing, but it's just the mathematical equation to calculate the percentage contribution from each of the sediment sources. And it takes a long time to run because it uses what we call a Monte Carlo uncertainty routine, where it varies the values it's inputting into the calculation to random values within the kind of range of the source samples we've collected from the catchment. And what we can do here is select the number of kind of iterations we want for that Monte Carlo routine. And I would suggest for most of the time just leave it at 1,000 because it can take a long time to calculate all this. Maybe when you're very happy with how your mixing model's running, you can increase it. But I know some computers will struggle if you start to increase it to like the 5,000 mark because it produces huge quantities of data. The other option you have here is this correlation coefficient required to class as correlated. So I just leave this as it is. I don't know I mean, it's been shown it makes some difference and can improve results. But what it's saying is if two traces are correlated within the source data sets you've collected, it makes sure that correlation is the same in the random numbers it's producing during this Monte Carlo uncertainty routine. So it gives you a much more realistic set of values going into the mixing model than you would get without this. So if you click the Mix Virtual Mixtures button, what it's going to do for now is, rather than just mix our sediments, it's going to put through a range of what we call virtual mixtures. So most of these are, say, the mean, or not the mean, the median value for each source group it will put down first, and then it will do kind of mixtures of the source groups that is calculated mathematically. So it will work out what the tracer concentration of a sediment sample would be if half the sediment came from, say, urban and half came from limestone. Put that through the model and then present us the results and say, we can look and say, is the model correctly able to recognize inputs of sediment from those two sources? It takes a long time to calculate all this, but it is, I kind of said earlier, source group classification might be the most important one. This competition is this one, because I did mention where we have things like sediment sources falling within a row in these biplots, such as for the 4 cluster and this geology one. And in that case, the mathematics might not work out. We might not be able to tell if it's like 50-50 contribution from 2 sources or from 1 source or any combination of various sources. So by running these virtual mixtures through the mixing model, we're able to check that it's accurately producing results for each sediment source. And you'll be very surprised, like very often it just won't pick up a particular sediment source. So we're back and it's finished running. It depends on what computer you're using, how long that one will take. I think this case it took about like 25 minutes. So what it's done is it's actually run the mixing model, each one 3 times, each using a different structure to this Monte Carlo uncertainty routine we mentioned. So the first one it did, it kind of sampled random values using a distribution of tracer concentrations which are roughly similar to what we'd sampled in the source data set. And I kind of used to use this one kind of as standard mostly before. We also did it a second way, that's sampling them according to a normal distribution based on the mean and standard deviation for each source group. And then a third way using this, sampling the values from between the 25th and 75th percentile range of each source group. And you can see just in the bottom here you've got 3 different graphs, each for the different distributions. So you can see, yeah, they're named by distribution here. So what we've done here, as I mentioned, is we've run these virtual sample mixtures, putting through known values, such as 100% contribution from each source, so the median for each source group, and then kind of various combinations of the different source groups. And what we want to do here is look through the results of those to see, are the composite fingerprints accurately identifying each of those sediment sources, and really, are they like producing accurate results? Because quite often you'll find certain combinations of source groups and traces and things just won't be able to produce good results. So if you scroll up to the top a bit,
yeah,
you can see here we've got two options. One says fingerprint, one says source groups. So at the moment we're viewing the 2 cluster source groups and the basic fingerprint for that. And you can see we've got these radio buttons where it says like 100% cluster 1, 100% cluster 2, just down. So yeah, there you go. So at the moment we're showing results for 100% contribution from cluster 1, which is the red one. And oddly, like most of the time, these cluster analysis source groups work very well, but in this case I think we've been a bit unlucky, and our basic composite fingerprint's not doing a good job at discriminating these 2 clusters, which actually is very unusual. I don't normally get this happen. So what it should look like is you've got on the x-axis contribution to mixture from a 0 to a 1, so 100% contribution. So the correct composition of this mixture would be the red bar entirely at the 1 level and the blue bars entirely at the 0. So what we call this is like a probability density function. So where you've got kind of a spread of bars, it means the actual true mixture composition in this case could be anywhere between kind of a 5% contribution from cluster 1 up to 100%. So it's really not a very good result. Try clicking the 100% cluster 2 button and see what that comes out as. There you go. So yeah, this is what it should look like. So we've got a mixture which is the median value for cluster 2. So we'd expect all of the contribution to come from that. And you can see that that's what we're finding, really. All the iterations are suggesting that. It just, for some reason, and it happens sometimes, you just get a composite fingerprint that doesn't work well. We're not recognising cluster 1 in this particular mixing model. So if you click the cluster 1 button again, the 100% cluster 1, what you can do is go to the fingerprint menu and change it to conservative or high variability. Conservative, no, that's not particularly successful. Try the high variability one. No, well, it just seems for some reason our 2 cluster model doesn't seem to work very well, which doesn't happen often, but it can happen. We've just ended up with a slightly dodgy set of composite fingerprints here, or perhaps we excluded too many tracers or something at some point, or the dataset just doesn't fit this 2 cluster grouping particularly well. So by looking at these, we kind of know we don't really want to be looking at the sediment provenance results we produce using these 2 cluster source groups, because they're not going to be very accurate. So if you change the source groups once to the 3 cluster, so this is a bit better. It should be. So this mixture is 100% contribution from cluster 1. So we'd expect all the red bars to be at 1. And you will notice here you've got some big differences between these distributions that are used. And almost always I find that this transform normal distribution type 1 performs very poorly, which is a shame because many mixing model frameworks, especially some of the Bayesian ones, will use a distribution like this. Interestingly, if you scroll down, you normally find it's this 25th to 75th percentile distribution works the best. Hopefully, I should have a paper on this published quite soon. It's about finished, so I won't go into details why. But I am tending to find that using this distribution, even though it's kind of truncated and you're not using the whole source data set, does work quite well. And you can see here, we've not got a perfect apportionment of this mixture, but it's really not bad. It's suggesting that by far that's the dominant sediment source, cluster 1, which is correct. So if you go back to the top, we just want to check them all. So try 100% cluster 2. I tend to find if these 100% ones work, they're all fine, but we can see, yeah, that's right. So all of the models are correctly identifying that as the dominant sediment source. And try the 100% cluster 3 one. And yeah, that works as well. So with cluster 1, it struggled with a little bit, but if we use the 25th to 75th percentile model, then that's fine. Now, I remember we said that the 4 cluster group was perhaps unlikely to work, so let's have a check of that. So cluster 1 seems fine. That 100% mixture is correctly apportioned.
Is it okay keeping it on high variability, Simon?
Yeah, I'd often check them all, but I tend to find with most of these, if it works for one, it often works for them all. But the model, I'll show you later, but the model will actually like select the ones it thinks you should keep and run and which ones you shouldn't, so it should be okay. Cluster, yeah, so you normally get this case where one source is just not picking out particularly well if you have too many source groups that aren't well discriminated. Oh, so actually that's a lot better than I thought it would be.
Yeah, that's not too bad.
Yeah, with the 25th to 75th percentile type model, it actually seems like we might be able to get something to work with that. Which, I mean, it shows those plots are only showing the 2 major discriminant functions, so they're not comprehensive. But try switching the fingerprint to another one and seeing if it's the same. Yeah, try, what was it, source? Try cluster 3 for the mixture, because that's the one we struggled with. Yeah, see.
Yeah, it's still struggling.
Yeah, it's not amazing. It's really underestimating that source. I mean, there may be something we can do about that on the next page. So we don't want to kind of totally throw away that model. It may be we can use it.
Yeah.
Let's try the land use and yeah, so as expected, urban's fine. I mean, they're so distinctive, that source, that we'd expect them to work.
Banks as well.
Yeah, Banks is okay.
Soils, not
yeah,
so much.
So that's the one. Yeah, because remember we said when we were looking at all the other data that discrimination between banks of soil really wasn't very good.
No.
And it's kind of showing we really need those as one source group. We can't really make it work with them as separate. And it's why it's kind of essential to do this virtual mixture step. I mean, even kind of, these have been used for the last few years, but less than half of papers actually include virtual sample mixtures. And it does make you wonder just how many studies are being published where they're actually not really able to discriminate between the source groups, but are producing results anyway. Well, that's not so bad.
No, so this is on geology now.
Oh, that one actually works.
All of them are pretty good, yeah.
Yeah, so you tend to find the more source groups you have, the harder it is to get a model that will actually work. But it happens this run of the software, and it can vary a lot between different runs of it, is producing quite good results for the groups with like 4 source groups, but the one where we've got 2 cluster groups, it's struggling. And I mean, a lot of this can come down to kind of some decisions you've made in the modeling or what random traces the discriminant analysis has selected. So if you run the model again, chances are we'd get slightly different on this. It's why it can be worth just running the model twice and making some slightly different decisions.
Yeah, make sure we get it.
Okay, so we have an option. Now we've looked at these, actually, let's go down slightly to the bottom of the page, or down all the way to the bottom of the page. So it gives you these tables, and it's the mean kind of error in the source apportionment. And I mean, we kind of looked at it and we said that 25th to 75th percentile distribution was working the best. Oh, slight typo in the name there. And you can see our mean errors here are all quite low. I mean, this is land use. I mean, we looked at the plots, and even though it's only 10% error, that error was that we couldn't recognise one source, so we didn't do too well there. But geology, 4 cluster and 3 cluster are all very low kind of errors there. The 2 cluster just failed. So what we need to do is look at these tick boxes in the bottom and untick any models where we're not actually going to use them and we're not going to be happy with the result. So if you untick all of the ones for the 2 cluster model, yeah, and land use as well, I mean, it might be worth keeping. Let's keep, maybe if you go to the top and have a look and see no, actually we don't need to do this. We can look at the table. So the land use conservative fingerprint was probably the most successful. Yeah, you can see there its errors like 8.53. Yeah, we'll look at those. I tend to just look at the one where it's got the best, where it's got the lowest error, so the 25th to 75th percentile normally, and kind of run with that, because you need to decide which of these model structures you want to use for the next stages of the software. So the others we're all kind of happy with, so we'll leave those in. Cool, so the next thing we can look at here, and I've included this as an option, but I found in practice it doesn't tend to make any difference, so I don't use it, but I'll show you it anyway. So if you scroll up slightly, slightly down, well, I've got these plots here, and when you run in a mixing model or one of the Monte Carlo iterations, it will come up with a value that's called goodness of fit. And it's kind of it's almost like an R-squared model, so it's how well your data fits the model. And what it's done is for each of these models we've run, it's calculated like if we were to exclude, say, a goodness of fit lower than 10 or 0.1, what is the overall error of the model on the y-axis. And we've got a plot here of how much of the goodness of fit you exclude, or what threshold you set to exclude below, and the overall error of what you're doing. And I tend to find it's normally like 1 or 2% difference once you start to exclude goodness of fits. But if you look at the plots on the right, it kind of shows you the percentage of the iterations that fail or fall below that threshold at certain goodness of fit ones. So once you start to exclude goodness of fits, you tend to delete most of your Monte Carlo iterations and model results for very little benefit. I mean, I've run this for about 9 or so data sets, and they're all about the same, but it could be that somebody runs this and has a data set and it does make a big improvement. So I'll leave the option in there to decide.
Just in case,
Yeah. So that's another thing that can be done. But so if you want to change that, the option's right at the top. There's a slider, and you can set it there anywhere between 0 and 50. But I'll leave it on 0 because I mean, you do find in the past, and even in quite recent papers, you get lots of people use this goodness of fit as a measurement of how successful the model is or how accurate it is. And unfortunately, that's totally wrong. I mean, you can see from these virtual mixture results, we could have like the 2 cluster model where it's really not recognizing one of the sediment sources, but that model is still likely to have a very good goodness of fit. So yeah, it has almost no relation to how accurate your results are. So but I mean, it's worth leaving in. I mean, it's what the mixing model part optimizes to come up with the best kind of combination of the sources contributing to your sediment. So I mean, it has function. Okay, so once we're happy with that, we've looked at all our graphs, we've decided which models will work and which won't. If you're a bit unsure and think maybe it'll work, maybe it won't, leave it in and run it. We can always delete its results later. So if you click the continue button, we get onto this page here. So what this page does, it lets you it reruns those virtual mixtures just for that 25th to 75th percentile model we selected. Also, I should have mentioned that if you quickly click back to virtual mixture results, see these buttons at the top. It's got 25th normal and sample-based distribution.
Yeah.
And that's where you select what distribution you want to use. Oh no, normally if you've been to a tab, don't click the button again to go to the next one. In this case, it's fine. Most of the pages in the so if you've clicked back, use the top buttons to click back to the page you were on, not the button again, not continue. Yeah, so just click the weightings. Yeah. So what we can do here is we can weight specific traces in the model to give them greater emphasis in the maths. So a key reason we might want to do that is if we've got something like urban as a source, like we had for land use, and then two quite poorly discriminated sources like channel banks and surface. So it could be that most of the traces really discriminate, or it is that most of the traces really discriminate urban from those other sources well, but we've only got one tracer that really discriminates topsoils from channel banks well.
Yeah.
And that's probably cesium 137 in this case. So what we'd want to do is give extra weighting to that cesium 137, so it's just not drowned out by, say, like 8 tracers that can discriminate land use brilliantly. So what it does here is, I mean, you can see it's ticked a few of these boxes for you already. And the way it comes up with this is if you click back to that compare sources and sediment tabs at the top, you can see it's produced these biplots. And just down to the plot, and you see function 1, it gives you slightly up. Function 1, it kind of gives you like the percentage of say in this case you've got 79.3% of the discrimination is provided by discriminant function 1, whereas discriminant function 2, if you scroll up slightly, it's like 18.4%.
Right,
so that's for one fingerprint, and it could be that 18.4% of the tracers is very important for discriminating, in this case, limestone, clays, and ironstone. So if you scroll down slightly to these tables you were on before, what you can see is these are the correlations of each tracer with each of these 2 discriminant functions. And you see most of them tend to be correlated quite strongly with LD1, so the first discriminant function, which is the one that discriminates urban and the other sources. But you have some of them, say like calcium here, is very strongly correlated with LD2. But that's only like one tracer really in that, so it's drowned out by all these other tracers that can discriminate like the urban from the others. So what we can do is any tracer that's in this LD2, or as we've been through when we looked at those maps of differences between sources and sediments to get an idea of what the tracers were doing there, and we looked at those plots of the tracer distributions with the different lines, any tracer we've identified has been particularly important for discriminating between some sediment sources. We can give them additional weighting in the model. So if you go back to the top and click back to the weightings tab, not the button, just the thing, perfect. You can see what it's automatically done is looked at that table we were just on and ticked the tracers most strongly correlated with LD2. It could be though we're only showing the 2 major discriminant functions. It could be there's maybe 3 or 4. Unfortunately the model doesn't show these at the moment, but we could identify them ourselves, and it could be we need to manually tick some more of these buttons.
So do we just click cesium?
So let's just look at land use and geology for now. So you can see for the land use one, we've got cesium 137 ticked, and zirconium ticked as another, because it'll normally pick 2, I think. We might not need the zirconium, but we'll leave it. And geology model, we've got calcium, which is obviously that discriminator of limestone. And actinium 228, which I don't think we looked at, but will discriminate something. So you can manually tick any more if we wanted to. I don't think we really need any more, but we could, if we were doing this properly and writing things down, we might have thought of some others. then there's these radio buttons here, select how much to weight by. So it's how much emphasis to give. So it might weight the cesium-137 5 times more importance than it currently is. I actually have no idea which the best number to tick this one at is. It could be you try this multiple times and just work out what's likely to be the best or not, but see, and there's also a weighting here which I don't tend to use, but it's an option. You can weight the tracers with that highest variability ratio. So the biggest differences between source groups and lowest within source group variability, like we saw on the summary statistics page.
Yeah.
I mean, I won't use this now because it tends to be this is really dominated by the presence of that really strongly discriminated urban source. So I think we best leave it as it's set up. So if you tick the test weightings button, what it will do is run the models. Again, it's not going to take as long as before because we're only running it with that 25th to 75th percentile distribution, but it will run the models again, applying those weightings. And then we can compare the results of the virtual mixtures before and after having the weightings and see if they've actually made an improvement or not. And if they have made an improvement, we can actually use that while I'm mixing our sediments to get a more accurate result. Okay, so that took about 5 minutes and we're finally done. What you'll find is when this finishes, it doesn't actually automatically update the screen, but the weighting dialog box kind of disappears. And the top button there goes blank. You see where it says like right at the very top next to 2 cluster under fingerprint. So if you click that and switch it to put it on basic perhaps, and then 2 cluster we're not using, so we can ignore, so it's not going to show the graph, but try land use, or 3 cluster will do. Yeah, so what you can do is click the button here to switch between the mixtures. So for cluster 1, the results are very similar, but I mean weighted looks slightly better, but that's about the same. And that's probably slightly worse. You'll find it varies a lot between data sets. I don't think this data set, the weightings generally make a huge difference, but I have certain ones where it can make kind of like up to like a 20% improvement.
Yeah.
So try geology actually. I mean, they're the ones we're really interested in. Okay, so our urban's probably a bit worse because we've got less at the 1 position, but it's still not bad. Limestone looks a bit better there, so the bars are more shifted to the right. Ironstone's very similar, isn't it?
Yeah, it's about the same, I think.
And clay's about the same, so yeah, it's not made a huge difference. I don't think it does on this data set, but others it might. Try land use. Okay, we were only going to run. Are we only running the conservative land use, aren't we?
Yeah, we were, because
so if you change where it says fingerprint, if you change that to conservative, yeah, there you go. Okay. So urban's a bit worse.
Yeah,
that's a bit worse.
That's not.
Oh, soil's better.
Yeah.
Yeah, see, we've got quite a big improvement. Well, a reasonable improvement there of kind of looking at discriminating soil and channel banks.
Yeah.
I mean, so we know our results, if we use this fingerprint, we know our results, we need to treat them with some caution, but we might actually be able to get some idea of relative contributions of channel banks and soils if we use this weighted model.
Yeah. What are the equal source
okay,
ones?
so I mean, I tend to just look at the first ones, but so if you click on one of them, equal source 1 and 2, so that will be urban and banks. Yeah. This is a mixture that would be like 50%. And you see here, the weighted ones actually made it a bit worse.
Yeah.
But so I mean, I tend to find if it can recognise 100% from each source, it tends to be okay. But it is worth looking at all of these other radio buttons. Maybe try equal source 2 and 3. Those are hard to discriminate ones. Oh yeah, that's not good. So we're going to really overestimate contributions from channel banks in that case, aren't we?
Yeah.
Mm. Yeah,
Yeah,
so that sort of model, I mean, we might use it to get kind of a qualitative idea as to what's the most important source, urban or banks, but it seems like we're probably going to really overestimate our bank contribution in the final result.
yeah,
So if you scroll down, I mean, if you change the source groups there to try 4 cluster, perhaps we haven't looked at that. I mean, it's exactly the same data, it's just presented a different way. So you've got modelled in the dark colour, modelled in the light colour, and expected in the grey, and it's just showing kind of basic fingerprints, 100% from cluster 1, 100% from cluster 2, and
yeah.
so on. So you can just see how close the blue bar is to the darker. And I tend to just use the top plots. We were looking at the histogram type ones, but sometimes these are nice to look at. I mean, it shows all the different mixtures all in one graph, so that's quite useful. And you can kind of see here, looking across, they're all very accurate, actually.
Yeah, they're really similar.
Yeah, I must admit, when I've run this software before, I don't tend to get such a good result for the 4 cluster one, and I tend to get a lot better for the 2 cluster one. So this shows if you try running it twice, you're probably going to get slightly better discrimination or worse. Or it really is worth just trying it multiple times. Right, so if you go right to the bottom now, lots of graphs there. Okay, and where it says show summary tables, if you just click on that white box and click yes. Okay, maybe click no and then click yes. I need to figure this out because I did struggle to get it to... There you go. Yeah, I do struggle to get it to update. So what it gives you here is the overall error associated with each one. And you've got unweighted there and weighted there, and you can compare them and see overall what the improvement is. And where there is an improvement, the model will automatically tick these checkboxes at the bottom to actually use the weighted one. So in fact, the weightings are actually at only 2 of the models. The weightings overall make it worse. So they do result only in about sort of up to a 1% improvement, but I mean, it is an improvement.
Yeah, that's good. Okay.
Yeah, so once we're happy with that, we can go up to the top. I mean, it's worth mentioning you can actually run this weightings thing multiple times. So if we weren't happy with these weightings, we could pick different ones, rerun it, see if it improved it more. But we'll just run it the first time and leave it at that. So next you want to click that sensitivity analysis button. And this is a new feature I've added in, and it's not really used in any... well, it will be used once I get my next paper published, hopefully, but it's not really used in many fingerprinting studies. But what it's doing is rerunning it for the virtual mixtures, but they're calculating them rather than saying like 100% of the contribution from source 1 we're representing with the median value. It will calculate it using only a subsection of the source samples you've collected for that source. So it might select only 10% of the source samples you've collected for source group 1, and then kind of run the model using the median of that. So it's really just testing the sensitivity of the model we're using to if sediment is contributed from only a very localized area of the catchment, rather than having equal contributions from all the sources we've collected. And again, you can run this as many times as you want. It will take, it'll probably take a bit longer than the weightings one to finish. But it gives you a nice idea of how robust your model is. Like what would have happened if you'd collected slightly fewer source samples, for example, or say you've got like a farmyard or farm track in your catchment that's just full of mud and contributing a really high proportion of the sediment to the river. Like how does that affect how might that affect the results of your model or its accuracy? Right, so we've just come back from running the sensitivity analysis, and I think that was what, 5 or 10 minutes?
Yeah.
Cool. Okay, so if you scroll down on this page, we'll look at that top graph a bit later. So what we want are these graphs here. And what it shows is on the x-axis is the overall error of the model for all of the virtual mixtures we ran, like we looked at in the table on the last screen. And in the bottom axis is the percentage of the source samples in each group used to form the virtual mixture we were looking at.
Okay.
And let's look at, say, geology. What you can see is the overall error of the model is quite low. It was something like 3 or 4% when...
Yeah.
But once you get to about 50% of the source samples you're using, that error increases to about 6%. And then when you get down to just using like 10% or so of the source samples, which might just be one sample for some source groups, your error is up to about 12.5%.
Yeah.
So it shows it slightly, I mean, if we were to have very kind of localized inputs of sediment from one source, we could start to get a much higher error in our model, but I mean, 12% is not terrible, and the chances of that actually happening in a real catchment are quite limited, so that actually looks quite good for me there. You can see like 3 cluster, it's a bit all over the place, but if you look at the values on the axis, the highest error is just over 5%, so there's actually no change, so we know that's very robust. Yeah. And 4 cluster, it increases as you use fewer source samples, but again, it only goes up to like 8 or 9%.
Yeah.
So, again, that's not so bad. You can check if you go down. It's got all the other fingerprints there. I mean, see there, 3 cluster for conservative. We've obviously had a particularly dodgy sample come out when we're using 80%, and it's 16. But it does seem. What I found, I've run this for quite a few different data sets. It tends to be only when you're using like maybe the bottom 10 or 20% of samples, or only, I should say rather, when you're only using 10 or 20% of the samples from each source group to make the mixtures, when the error starts to appear.
Okay. Yeah.
So I mean, it's worth looking at those because it does show you could potentially have, like, if you're making your virtual mixture app using the whole tracer data set and assuming like uniform contributions from each source, you could think, oh, the uncertainty is very low in that way, but then you could run this and find out, oh, if you're using only kind of like half of the source samples or not assuming an equal contribution, you could have quite high errors hiding in the background. So I mean, it's not, we don't really reject any models at this stage or anything, but it's a useful thing to look at to really understand kind of how robust your results are likely to be. If you go back to the top here, you can see what you can do. I mean, it's not the most useful interface in the world because there's so many models being run, but if you wanted to look at a particular one, so here we've got the basic fingerprint 3 cluster source grouping, and we're looking at a virtual mixture of 100% of source 1. And all these radio buttons here are the results produced using different fractions of the source sample data set. So at the moment, we're showing 100% of sources. So if you click down and maybe try the 10% of sources one, you can see how the result changes. So actually it's better if you're using. But maybe click through them and see how it changes. Try the 20 and see 20% of sources look like that. So you can just see how the how well recognized each source is and how that changes with just using like a lower percentage of the source sample data set.
It's strange that 10% is like that, isn't it?
Yeah, I mean, what you'll find is when you get to 10 or 20%, it tends to just be one sample. So there is a bit of randomness to it.
So that one sample, but it's chosen, happens to be really discriminate.
Yeah, it could be you pick a weird outlying sample and the result's just useless.
So
what you can do on this is run this sensitivity analysis multiple times. And if you scroll right to the bottom of the page, you see it gives you a table here of the summarizing the overall error. You'd need to multiply them by 100, but if you wanted to run this sensitivity analysis, say like 10 times, you could copy this table each time and come up with like an average and stuff in Excel.
Average,
so that option's there. But we've looked at this and it's like most of them look fine to me. We're not getting kind of huge spikes in error. I mean, it might
No.
double it or so, but they're still reasonable enough. So
Yeah.
once we're happy with this, we can go back to the top and click the Unmixed Sediments button, and these are the last models we have to run. Again, this is going to take 10 or so minutes. It will depend on how many sediment samples you've got, how many source groups, and how many tracers. Sometimes it can be very fast, other times slower. At most, you're allowed to have about, I think it's 50 sediment samples at a time.
Okay.
I find virtually no one ever has more than that. But if you have more, you'll probably have to break it into different parts and run the model multiple times.
Yeah. 50 is quite a lot anyway, isn't it?
It is, yeah. And if you have that many, the graphs just don't come out looking particularly good. So, okay, we're back after another 5 or 10 minutes, and all the sediment unmixing is now done, and it's moved us onto this Goodness of Fit tab.
Yeah.
So we didn't run the 2 cluster model, so we've got a blank space there where the graph would be. But what this is showing here is we set that Goodness of Fit threshold as 0 back on the virtual mixtures page where we saw the results. And it's telling us the percentage of the Monte Carlo iterations that have passed that threshold when unmixing the sediment samples. So like I mentioned, Goodness of Fit isn't really an analysis of how accurate your model is, but it is a measurement of how much in agreement the tracers you've used are. So if you have a very low Goodness of Fit, it kind of suggests that the tracers are trying to tell you some different things. That might not necessarily be a problem, but if these are all quite low, it might be you want to look back at your tracer data set and try and work out, have you got one tracer that's perhaps trying to tell you something different? Or, I mean, one nice example might be, say, if we're doing the 3 cluster solution here, where our source groups are ironstone, urban, and the rest. If we've got one sample that's had a big input of limestone in it, which isn't represented in the source groups, we'll have calcium coming out with some really weird results for that source group classification. And because it's coming out with those weird results that aren't the same as the other tracers we're using, the Goodness of Fit will be lowered. So in that example, that's not necessarily a problem, but it does tell us something about the source groups we're using and the tracers we're using. Which we might bear in mind when looking at the results or considering running it again, perhaps with some different source groups. So if you scroll down, we can kind of have a look at these, and they're all quite high. We only run the one land use model, but they're quite all reasonable. You do get some samples where there's kind of bits of dip, so we're getting a lower one. I mean, one reason we could get those is if we've got, say, a non-conservative tracer as well, where a tracer's being altered during the sediment transport or storage somewhere. And in that case, the low Goodness of Fit might indicate that, but you'd have to go back and look at the biplots and the data you've got to try and work out if that is the case. But I mean, generally, like, there is the option at the bottom, you can reject some models on the basis of the Goodness of Fit if it's always bad. I don't tend to do that. I'll tend to let them all through. But if, for example, say for like the height, like you had one source group classification and one fingerprint and all the Goodness of Fits were terrible, you might just want to discard that one. Okay, so if you keep scrolling down, we have these graphs, and it's of the models that pass the Goodness of Fit threshold, what is the median Goodness of Fit of those? So higher is better, but again, lower doesn't necessarily mean there's anything wrong. So if you go right to the bottom, or right down. So these pie charts, I used to use them quite a lot with some other data sets I've used, but since I've used this software, it's not particularly coming useful. But what it shows is the contribution of each tracer to that overall Goodness of Fit. So if you have, say in this pie chart, most of the pieces are roughly the same size. I mean, we haven't got like one huge chunk that's massive and the rest are all quite small. So it means that all the tracers are contributing equally to it. But if we were to run it and we had like one tracer took up over half of the pie chart and all the other like 8 or so were quite small, we'd say perhaps that one tracer that's contributing all that much to the goodness of fit is a problem. Perhaps it's non-conservative or has a different message to the other tracers. So it might give us some idea to look at that particular tracer and maybe remove it in future model runs or something like that. But if you scroll down, I don't think there will be any like that in there. Yeah, they're all fine, I think.
Yeah.
I mean, I have color coded them. The colors aren't great, but each tracer should be the same color in all of the pie charts. So if you see like in one model, one tracer's causing a problem, and then in two more, it's also causing a problem, it's more evidence that that particular tracer is something wrong with it.
Yeah.
Cool. So at the bottom, there's tick boxes where you can reject any models based on goodness of fit you want to. I don't generally do that, like I said earlier. So we'll leave them all blank for now. So if you click the button there, view results, we finally have got there and have some sediment provenance results. We didn't run the 2 cluster model, so we don't have a result there. But if you change that to 3 cluster, where we have, and what you can do is change where it says sample, you can click between them. So here we've got cluster 2 is contributing all the sediment, which can't remember. If you click back to the maps tab, we'd be able to work out what. Actually, I do know what that one is. That's the clays, isn't it? It's not ironstone and not urban. So if you click through the samples, we can kind of see how it changes. And one thing I should have mentioned is this sampling. It kind of roughly the samples go from T1 is one in the headwaters of the catchment, and it goes downstream roughly as you move through. We'll see in the next screen, it shows you a map of the catchment where I've marked on where the sediment samples are collected, so we can get an idea here. But try land use or geology. Land use where you need conservative.
It's geology, isn't it?
Yeah, land use conservative.
Didn't we? There you go. Wow, okay, so clay again.
Yeah, that's what I'd expect.
So it's consistent with the cluster source groups too.
Yeah, you will get some variation between these.
Yeah,
and you will occasionally just get one result or two that just seems a bit dodgy, but you want to look at all the samples together and just get a general idea of what's going on. And it's really saying, that clay source is really the dominant one. Yeah, Wellingborough is where you're getting towards the east of the catchment, and you do have the limestone deposits.
Further downstream.
Yeah, so you'd expect to have a higher contribution from it there. And Ditchford at the end, that's right on the main stream of the river, and it's kind of like represents the whole basin.
Yeah.
So the clays are dominant, and so if you scroll down slightly, you've got another. Change that to try land use. We haven't looked at that. Yeah, it's another way of showing the graphs, but it shows all the samples. I've only got conservative, but it shows all the samples together. So we know this result's not the most reliable, and from the virtual mixtures we've seen, we're likely to be overestimating the contribution of sediment from channel banks. But it is really suggesting that channel banks are the dominant sediment source, apart from maybe in this Wellingborough sample here, and we've got like bushlands and Cookno, where you've got a little bit of an urban contribution, which you'd expect because that Wellingborough sample was taken in a stream running through a town, and Bushlands and Cookno are downstream of the town of Northampton, so you've got urban street dust centering there.
That makes sense.
I have done some other analysis looking at like cesium-137 activities in the sediments and sources, and I do kind of know from that that this is right. The channel banks are really the dominant sediment source within this catchment. Main reason is that connectivity between like fields and the rivers is effectively like next to zero. There's no obvious way that sediment can move from the fields into the river unless it's like the rain is just heavy enough to really breach thick buffer strips. And the soils also are very clayey, they're not highly eroded. And if you go to the geology one and we have a look at that, Yeah, there you go.
Clays, yeah.
Yeah, you can see it's slightly different there. We have got more of a limestone contribution to some of them, but it's not overly high, is it? And you see the two composite fingerprints here. We've got conservative, basic, and you can see there is a difference. Like the basic and high variability aren't picking up that urban contribution quite, whereas the conservative is. And it's not particularly reassuring seeing this, but it is often the case that you will get slight differences between these composite fingerprints, and you do need to use kind of a bit of know-how to interpret the results and what's likely to be correct and not. But I mean, looking at the two, I mean, the urban contribution is very low, apart from in the one sample anyway, so it's not really going to change our conclusions having these differences. But you notice there's no ironstone contribution, which I mean I did find surprising because the ironstone soils are much more sandy and easily eroded than the clays.
Yeah.
But it's just the way the catchment geology works is that the ironstone is often very distant from the river, so the sediment would have to travel kind of hundreds of meters to actually get from that field into any sort of river channel. You've got a big buffer of clays and often flat land between it, so although erosion might be quite high, and I've seen rilling on those soils, the sediment just can't get into the river.
That's right, yeah. I can imagine it's a different case with a lot of other catchments.
Oh, it is, yeah. And the Nem Basin's really weird. Like, virtually nowhere else has so much of a contribution from channel banks and so little surface. But it's an interesting one to study anyway. So if you go back to the top, I think that's... and click View Mapped Results. Might take a while.
That's okay.
Yeah, there we go. Right, so yeah, if you change that to 3 cluster or something. So what this does is, it's perhaps not the most scientifically robust way of doing this, but it takes those sediment provenance results we've got and produces and overlays them onto the map of the catchment, kind of color coding each individual source sample by the contribution of its source group. So you can see any red sample has got a contribution of 100% of the sediments come from that area, and any blue is 0%, and then you've got various values in between. So it's a really nice visual way of showing results. And you can see the urban samples we've got, and the ironstony ones we've got the no contribution there.
Yeah.
So if you look down, there's all those radio buttons, and you can click. This is showing the result from sample T1, and you can see on the map I've kind of marked it there. I've actually drawn it onto the ArcGIS map I input into the software, so you can see where T1's located in the west of the catchment there too. So it's quite a useful way of doing it. I mean, I will eventually, in some later iterations, allow kind of you to put in coordinates for the sediment samples, but it's not the easiest thing to get consistently working and making the graphs look good. So if you go down past that, you can obviously switch between the samples, but this takes all the models that we've run and we've kind of decided produce accurate results. It takes the result and averages its contribution. So let's say each of these points on here is a source sample, and it could be in the 2 cluster source group, it could be in source 1, in the 3 cluster it could be in source 3, 4 cluster it could be in source 4, land use it could be a topsoil. And it will take all the sediment provenance estimates from all of those sources and average them together, and it comes up with like the average contribution of that particular sample and its groups to the sediment, which means scientifically it's perhaps not the best way of doing it, but to come up with like an end result for this software which shows you the sediment provenance results, it comes up with this, and it's kind of almost like a heat map of where sediments are most likely to have originated from.
Yeah, that's really useful for, if you wanted to show farmers or anyone this data. I think that's a really visual way of showing that to them.
Yeah. So if you try clicking something, maybe click on the Ditchford button at the end. Yeah, that's the one. And yeah, you see it changes. So Ditchford is the one right on the outlet of the catchment, and you can kind of see a nice band of yellow and orange samples where the sediment's likely to have come from.
Gosh, so
Yeah.
right over the other side.
Yeah, I mean, one downside to this is it does kind of require you to have collected a lot of source samples scattered over the whole catchment, which many projects just won't have the budget to do. And even in this map, you'll see lots of gaps where I've just not collected any samples.
Yeah.
So even here, we probably don't quite have enough samples to look at this robustly. I mean, in my more recent projects I'm doing now, I actually have tried to cover the whole catchment. So it's slightly dependent on how many source samples you've collected and where from.
Yeah.
But I do like it. It's a nice visual way, and you see at the bottom it lets you can click the buttons and highlight specific sources as well. Yeah, try banks. That's a good one.
Yeah, I think Sediment doesn't contribute much. So
there you go. So it turns all the channel banks a certain colour.
Yeah.
Yeah, so it just gives you that extra, rather than just, I mean, in a more conventional methodology, you just might use one source grouping like land use and run all the models for that. And you'd perhaps say there's a 50% plus or minus like 20% either way contribution from channel banks or something. With this, you can really start to narrow down which areas of the catchment are likely to be contributing the sediment from the channel banks as well. So you get a much more spatially precise idea of, like, if you're wanting to do some like mitigation options and some work in the catchment, you can really start to point down to certain areas to do that work in, rather than just like channel banks over the whole thing.
Yeah. Excellent.
Cool. So if you go back to the top and click finish. There we go. So I put in here some suggested references for various parts of the methodology. These are no way like complete. I mean, there's loads of other studies that have done stuff like this, but I've put in what I can remember and what I think the key papers for different parts are. So if you want to like cite them, if you're publishing things, then they're there for that. And we've also got the R packages that have been used to produce this software as well. So thanks for all the people who made those. I think that's it. It's taken many hours, but we've been through and done quite a robust fingerprinting exercise, and you can see we've hopefully understand like exactly what our tracers are trying to tell us now. And I mean, we could even go through now, we've run it once and run it again, but using the knowledge we've gained, and see if we could get a better result.
Yeah.
Cool. But yeah, thanks Charlotte for helping out with this. It's hopefully it's been informative for you.
Yeah, no, it has been. Yeah, no problem. Yeah, I enjoyed learning about sensitivity analysis, which is something I haven't seen before within SIFT, so that was interesting. But yeah, and I hope that this video is really useful for people learning how to use SIFT.